We have discussed the difference between heat and temperature in a previous podcast. Now we will define what is meant as a state or phase of matter. Most people have come across three basic states of matter: solid, liquid and gas. There are other states of matter and different types of change between state of matter. In our discussion, we will limit ourselves to first order changes of state. These are easily seen if you carry out a really simple experiment. You will need one pan, one tap, one freezer, one gas heating ring, one thermometer and one stopwatch. First of all, half fill your pan with water and place it in your freezer. Leave it in your freezer overnight to make sure that the water has all turned to ice. You could do this with ice cubes, but I would have had to add more stuff to my equipment list. Now, take the pan and place it on your gas heater ring. Place the thermometer in contact with the ice and record the temperature. Turn on the gas ring, light it and start your stopwatch. Record the temperature of your ice block every minute. You should see the temperature rise from minus values up to 0 degrees C-ish. I say ish because water contains impurities, and so won't be exactly 0 degrees C when it starts to melt, just somewhere near. At some point, you should notice your ice starts to melt. If you've been recording the temperature every minute, you will see that the temperature rise of your ice has stopped. At around 0 degrees C, the solid water undergoes the defining characteristics of a phase change. It changes from one state to another. You can't see this phase change clearly with your eyes. That's because it takes energy for a material to change from one state to another. Observing your heating pan of water, you will see some liquid and some solid. The material is a state of change from one to another. This change is discussed more in the next podcast, but for now we can simply say that this is the defining boundary of a phase or state. A state of matter exists either side of a phase transition. Below this phase transition, the state is solid. Above it is water. With more energy, you can reach the next phase transition of liquid to gas, and again you will see that temperature flatlines as energy increases. Why stopwatch? Well, the assumption in this experiment is that the rate of burning of gas is continuous over time, and so the rate at which energy is supplied to the water over time is also kept constant. In between phase transitions, you can use the data you've collected to work out some properties of heat, energy and time. If you plot temperature against time, you can see the phase changes and the dynamics of the system involved in your experiment. You can see that temperature increases over time within a state of matter, and that this increase appears to have a constant rate. That is about as far as you can go with this data, unless you have the calorific value of the gas you're using and the flow rate of the gas as well. If you do, then you convert the time axis to an energy axis and show that the energy input to a material within a state of matter is linear, i.e., it has a constant gradient. You would need to do 2 more experiments to show the complete relationship between energy and temperature change inside a state of matter. You would need to vary the mass of water involved in the experiment, and would also need to change the type of material used, e.g. alcohol or steel, or other such materials. These experiments are much more dangerous, so best not done at home. However, you will see that the relationship between heat, energy and temperature change inside a state is equal to the mass of the material used times the change in temperature times by a constant value. The constant value is different for different materials. You can show this by using the same mass of a material and change the material used. The different materials have different gradients, because they have different bond strengths between particles, but this value is constant as long as you stick to that material. It is called the specific heat capacity. It has a symbol C and has units of joules per kilogram per Kelvin. So after bringing together all these experiments, we can say that the relationship between heat, energy and temperature within a state of material is heat energy into a material equals the mass of the material times by the specific heat capacity for that material times by the temperature change measured of that material.